welcome back to Unit 3, Area of Study 1, Biology. We're looking at reactions and enzymes today. Indeed, correct. I can read. Let's skip a few of the introductory slides, some of this jazzy stuff, molecules and whatnot. Let's skip that. Let's look at this. We've got different types of chemical reactions. Of course, this is relevant to enzymes because enzymes help drive the chemical reactions. So, a few different terms that you need to know in relation to chemical reactions, and we might have seen some of these already before. Maybe not. Anyway, we can class chemical reactions as either being catabolic or anabolic. Catabolic reactions involve the breakdown of molecules into smaller molecules. So you take a large molecule, you break it down, that's a catabolic reaction. Anabolic, the opposite. Anabolic reactions involve the building up of larger molecules from small ones. Take something small, add it to something else small, get something bigger, that's an anabolic reaction. Always remember these because anabolic steroids, you know, people take them if they want their muscles to be nice and big, bodybuilders or whatnot, and you know, they build up their muscles, so anabolic reactions are the process of building things up. And then catabolic, I kind of think about it like my cat causes me to have a breakdown because it's always meowing and stuff, so catabolic reactions are all about breaking things down. That's my way of remembering it anyway. Catabolic reactions are exergonic. Exergonic means, down below here, exergonic reactions have an overall release of energy. So if you have a catabolic reaction, break something big apart, then energy will get released in that process. Anabolic reactions are endergonic, which is the opposite. If you want to build something up big, then you need an endergonic reaction. Exothermic and endothermic below can pretty similar, it's just energy in the form of heat. Now, we've already seen these reactions, and in fact we've already looked at condensation and hydrolysis reactions, which are examples of anabolic and catabolic reactions. Condensation, building up of a large macromolecule, is anabolic, it requires energy, and the catabolic reaction is hydrolysis, that breaking down of the large molecule, and that will release the energy. So we've seen examples of those, and we will continue to see more. Skip that one, don't worry, just ignore that other slide. Okay, we need to know about enzymes, and really the next couple of slides, next few slides are just dot points of the key facts that you just need to know about enzymes. There's no two ways about it. So, enzymes are protein molecules that act as catalysts to speed up biological reactions. You could use that as your definition for enzymes if you like. You know, it's right there for you. Feel free, take it. You don't have to credit me even. It's all yours. Heck, I probably copied it from someone anyway, so no credit required. It may not be the most succinct definition, but it explains everything we need to know. It tells us that enzymes are proteins. Great. It tells us that they're catalysts, so they make something happen, and it tells us that they speed up biological reactions, so the exact thing that they do. By that we mean, by speeding up biological reactions, they take reactions that would normally never occur or would occur so slowly that it's just bad news, and they speed them up. Yeah, some things in our body would just happen far too slow if it wasn't for enzymes. We would just not survive. Enzymes are there to make reactions happen faster. So I'm sure there's lots of analogies you could draw there, like whatever. I'm not going to go into that. Enzymes are not consumed during the reaction. That's another key point. That means that one enzyme molecule can be used over and over and over and over again to perform the same reaction. It might take a while if there's only one enzyme molecule, but it could break down many other molecules or perform many reactions. They're not consumed, they're not used up in the reaction. The next one, the compound on which an enzyme acts is called the substrate. So just the name for the thing that the enzyme is breaking down or building up is the substrate. When that binding happens between the enzyme and the substrate, it's called an enzyme-substrate complex. Makes sense. Enzymes can break a single structure into smaller components so they can perform a catabolic function. They can break it down, or they can be anabolic. They can take two smaller things and join them together. So two functions there. Also, there is a picture of a pineapple. Why is there pineapple? You work it out. Okay, enzyme examples. You don't need to know the names of these enzymes. You know, you don't necessarily need to know the specific names of any enzymes. You'll pick up a few. You'll certainly learn them throughout, and you'll learn them in relation to different processes, and you probably already know a few. I guess the only reason I've got this in there is to remind you about naming of enzymes as much as anything. You notice that apart from pepsin, of course pepsin has to break the rule, thanks a lot pepsin, but everything else on that list ends in ASE, and enzymes, most of the time, the name of the enzyme ends in ASE. So it's really easy to spot an enzyme if you've got a lineup of different words, because the one that ends in ASE is probably the enzyme. Often as well, the start of the name, often but not always, often the start of the name tells us what that enzyme breaks down. So lactase breaks down lactose, that disaccharide found in milk. It breaks it down into its two components. DNA polymerase makes a DNA polymer. It makes a new DNA polymer. RNA polymerase makes an RNA polymer. And lipase breaks down lipids. So you can learn a lot from the name of an enzyme. In fact, you can often predict what the name of enzymes will be. I think we've even been asked that in exam questions in the past. What would the name of this enzyme be? And they tell us all the info, and you just put A's on the end. It's really straightforward. Okay, a few more dot points about important things to know about enzymes. Enzymes have got an active site, this special particular region. It's like a little pocket or a cleft in the molecule. Here it is here in the top right. It's this indentation on the molecule. That's where the business happens. That's the action zone. That's not a term to use. That's just something that I came up with. It's a pretty good term though. Okay, so that's where the substrate binds and the reaction occurs. The shape of that active site is specific to different substrates. That's why I would say that enzymes are substrate specific, very important term as well. Each enzyme can generally only fit one type of substrate, with a few exceptions of course, because this is biology and that's just what biology throws up all the times. But most of the time we would consider them to be quite substrate specific. So the enzyme that breaks down maltose, a disaccharide sugar maltose, the enzyme, strangely enough, its name is maltase, it will only break down maltose. It can't break down lactose. Even though lactose is another type of disaccharide, it's got no chance. It can't break down sucrose because it only breaks down maltose. It is a substrate-specific enzyme. The shape of that active site only recognizes maltose. It doesn't know no sucrose. So it just don't fit. And the shape of that active site comes back to the tertiary structure of the enzyme, the protein, the tertiary structure of that protein. So we looked at that when it came to protein structures, levels of structure. Primary, secondary, tertiary is the important one for enzyme shape. That creates a specific active site. Okay, two different models in these two slides for looking at enzyme action, lock and key model and induced fit model. There's really not much to them. They're both very similar. The only difference being the lock and key model posits that the shape of the active site is 100% fit for the shape of the substrate. This is an old school model and it is no doubt not accurate because there's a number of things that suggest that that can't be the case. But just learn the steps. It's still worth knowing because just because. We'll talk about that, why. So it posits that the shape of the active site fits the shape of the enzyme, reaction occurs, it can be catabolic or anabolic. In this case it's catabolic because it's breaking down. Induced fit is a bit more modern and it tells us that the shape of the active site is not necessarily 100% accurate or 100% matched to the substrate, that the shape of the active site can change. The enzyme can mold or around the substrate, or its fit can become induced, so it can change as it meets the substrate. Here it is showing an anabolic effect, but it also could be catabolic. It could break molecules down as well. After it's done the reaction, the enzyme would then return back to its original shape. This model helps us to explain how some enzymes can fit a few different substrates. Some enzymes are not 100% substrate specific. They can work with a few different things, perhaps because of the induced fit model. Oh, look at this. Awesome animation. This is one of my early works, I would assume. Wow, look at that. Induced fit, catabolic reaction, and then blah, it just spits out the products. That is some classy animation right there. We'll look at that in class, leave that. We'll leave that for now, it's just repeating. And this is, so part of enzymes, I'll give you the lowdown, I'll give you the straight up. Part of what you need to know with enzymes is those facts about basic what an enzyme is and how it does its business, how it goes about reacting. And then the other key part you need to know is the factors that affect the enzyme reaction rates. So what affects how fast an enzyme will turn its the reactants into the product, or the thing that it starts with into the thing that it wants to end with. And there's going to be 6 different things that we need to be across here. Seems like a lot, but most of them certainly make sense. 2 of them are on this page, enzyme concentration and substrate concentration. Next 2 are probably on the next couple of slides. The temperature and the pH, and the last 2 are a bit later on, and that is the presence or absence of inhibitors, things that can mess with the enzymes, and the presence or absence of coenzymes or cofactors, things that can potentially help the enzyme. So 6 different things that we want to cover there. First 2, enzyme concentration and substrate concentration, should be pretty straightforward. As the concentration of enzyme increases, the rate at which the reaction occurs increases. So if I had a beaker full of maltose and I put 1 maltase enzyme in there, it's going to take a while for the reaction, all the reactions to occur, for all that maltose to get broke down. But if I put several hundred maltase enzymes in there, the reaction would occur much faster. Substrate concentration is similar. If I have a little bit of substrate, the reaction won't happen very fast. If I put a lot in, it'll happen much more faster. We'll come back to these 2 a lot more in class, because our next SAC will be around focusing on these 4 different factors that we'll look at right here. Next one was effective temperature. Because enzymes are proteins, they are affected by temperature. You push the temperature too high, you might denature the protein, and then it will lose its special shape. That means the active site loses its specificity, can no longer fit the substrate, can no longer do its job. We'll talk about lower temperatures there as well too. I just want to skip through these though and just flag them for now. And the effective pH, enzymes work best at a particular pH, and that really depends on the environment that they're normally found in. If you push the pH too high or too low, that enzyme's not going to like it. You push that enzyme really far and the enzyme's probably going to denature even. And then inhibitors, don't want to focus too much on those, but we might just cover them off in class. So just be aware that these substances called inhibitors, and they're often drugs or heavy metals, toxins, can sometimes get in the way of the enzyme. So you can see here that the substrate normally binds with the enzyme, but this yellow orangey colored thing is an inhibitor, and what that is doing is blocking the active site. It's sitting in the active site, occupying it, saying I'm not going nowhere, and the substrate can no longer bind with the enzyme. So it's an inhibitor, and obviously that's going to slow the reaction rate. That's going to slow down how well the enzyme works. And there's 2 different types of inhibitors shown there, and another couple of classes of inhibitors. I probably want to cover the rest of that stuff in class, because a lot of new concepts and more conceptual type things as we go there. So that'll be the end of my video, but I'm going to, I've got a musical outro to play on here. I don't know nothing about the technologies though, so I'm going to play it on my iPhone. It is of course Mr. W, straight out of YouTube, and we might have heard this one before. Mr. W's Enzymes rap. It's pretty good stuff. Check out his video on YouTube. In fact, I could put the link in the video. I could embed it in this video if I knew how to do it. And then I've seen lots of YouTube videos and they normally point to the link. So I go, if you like this song, click on the link right here. Or here. There we go. That's unlike the regular PewDiePie of biology videos or something like that. Alright, I'm going to keep listening to my song.